650 light-years away, a star 16 times heavier than our Sun is shaking. Its surface ripples, its core fuses carbon in its final death stage. And in July of 2025, scientists found a hidden companion buried inside its glow, a partner being slowly devoured. You're about to see what happens when Betelgeuse explodes. The flash that outshines the full moon, the neutrino flood that hits Earth before the light does, the shoulder of Orion gone forever. If this kind of cosmic story pulls you in, hit subscribe so you don't miss what comes next. Brace yourself. We begin. Step outside on a clear winter night and look south. You'll find the easiest constellation in the sky. 3 stars in a tight, straight row form the belt of Orion the Hunter. Now look up and to the left of that belt. You'll see a star burning a deep, angry red. That is Betelgeuse. And it's dying. Most stars in the night sky look white or blue or pale yellow. Betelgeuse looks like a drop of blood pinned to the dark. The colour isn't a trick of the atmosphere or your eyes. It's a warning. Red stars are cold stars, and cold, in the world of suns, means old. Betelgeuse is so old that it has begun to swell, bloat, and lose its grip on its own outer layers. If you swapped our Sun for Betelgeuse, the change would be cataclysmic. Mercury would vanish inside it. Venus would vanish inside it. Earth would vanish inside it. Mars would vanish inside it. The surface of Betelgeuse would reach almost to the orbit of Jupiter. Our entire inner solar system would sit, completely buried, inside one single star. It is the closest red supergiant to Earth. 650 light-years away sounds far, and it is. Light from Betelgeuse you see tonight left the star around the time knights still rode in armour. But on the cosmic map, 650 light-years is the next street over. Every other red supergiant astronomers know about sits much, much farther away. Betelgeuse is the giant we can study up close, the giant we can almost touch with our telescopes. It is also the giant we can watch die. Betelgeuse weighs around 16 to 20 times the mass of our Sun. That number alone is a death sentence. Stars that heavy don't live long. They burn through their fuel like a fire fed with gasoline. Our Sun has another 5 billion years left. Betelgeuse has, at most, a few 100,000. At minimum, possibly tens of years. Nobody knows which. Astronomers track it the way doctors track a patient with a failing heart. They watch its brightness, its pulses, its shivers. They listen for tiny changes that might mean the end is close. And lately, the patient has been behaving very strangely. In 2019, something happened that no living astronomer had ever seen. Betelgeuse darkened. Not by a small amount. It dropped to less than half of its normal brightness. People around the world looked up and saw the shoulder of Orion almost gone. Some of them held their breath, certain they were watching the start of the end. They weren't. But they weren't completely wrong either. That dimming was a clue. A loud, bright clue that something inside this star was changing. Something was reshaping its outer layers. Something was throwing off curtains of dust thick enough to dim a star you can see from 650 light-years away. For decades, scientists suspected Betelgeuse was hiding a secret. A second body, a partner star. They searched for it with Hubble. They searched for it with X-ray telescopes. They found nothing. Then, in 2025, they finally saw what had been hiding all along. And what they saw changed everything we thought we knew. December 2019. Astronomers around the world began emailing each other the same urgent question. Was anyone else seeing this? Because Betelgeuse was vanishing. For 150 years, humans had been recording how bright Betelgeuse looks from Earth. The records went back to the days of paper logbooks and brass telescopes. In all of that time, the star had never done anything like this. It got dimmer, and dimmer, and dimmer. By February of 2020, Betelgeuse had lost roughly 2/3 of its light. From the ground, the change was obvious to the naked eye. People stepped outside, looked at Orion, and saw a constellation with one shoulder almost gone. The hunter looked broken. Scientists called the event the Great Dimming. The internet called it something else. The internet called it a death rattle. A wave of panic and excitement rolled through stargazing communities. Forums lit up. Articles ran with headlines asking if Betelgeuse was about to explode. People imagined waking up one morning to a second sun in the sky, brighter than the moon, visible in broad daylight. The idea was thrilling and terrifying at the same time. Astronomers were a little more careful, but only a little. They couldn't rule it out. A star this old, behaving this strangely, could be in its final stages. The Great Dimming might be the curtain rising on the most powerful event humans had ever witnessed in real time. Then, slowly, Betelgeuse began to brighten again. By April 2020, the star had recovered most of its light. By later that year, it looked almost normal. Then it kept brightening, eventually becoming brighter than astronomers had ever measured it before. The supposed death rattle turned into a strange, uneven heartbeat that nobody fully understood. So what had really happened? Researchers turned every telescope they could spare onto the star. The European Southern Observatory used a powerful instrument called SPHERE on the Very Large Telescope in Chile to take direct images of Betelgeuse's surface. What they found was breathtaking and unexpected. One whole side of the star looked dim. Not all of it, just one massive patch on the southern half. Imagine looking at a face and seeing one cheek normal, the other cheek covered in shadow. The cause turned out to be a giant cloud of dust, a piece of Betelgeuse itself. The star had coughed. Massive stars constantly throw off material from their outer layers. They lose mass to space the way a melting snowman loses water. But this was something bigger. A huge plume of hot gas had been blasted upward from the star's surface. As it climbed and cooled, it condensed into a curtain of dust grains that blocked our view. We weren't watching Betelgeuse fade. We were watching one of its own explosive belches drift across our line of sight. That answer comforted some people. It frightened others. Because here is the question the dust answer didn't solve. Why now? Why this big? Why this violent? Healthy stars don't usually cough up enough material to dim themselves by 2/3. The Great Dimming wasn't a death. It was a symptom. And it was a sign that something deeper inside Betelgeuse, something hidden under all that fire and gas, was beginning to come undone. The dust cloud had a story to tell, and astronomers spent years reading it. When Betelgeuse threw off that massive plume in 2019, it didn't just block our view. It left fingerprints. Spectroscopic data, infrared images, and ultraviolet readings from the Hubble Space Telescope all caught pieces of the event. Slowly, scientists pieced together what had happened on the surface of a star they cannot land on, cannot touch, and cannot look at directly without burning out their instruments. Picture the surface of Betelgeuse like a violently boiling sea. But instead of water, this sea is made of plasma, gas so hot the atoms have been torn apart. Bubbles the size of our entire solar system rise and fall on this surface. Each bubble carries hot material from the inside up to the cooler outer layers, releases its heat, and sinks back down. This boiling process is called convection. On our Sun, the boiling cells are tiny. On Betelgeuse, they are unimaginable. In late 2018, one of these convection cells appears to have surged upward with extra force. At the same time, a natural pulsation cycle inside the star caused its surface to bulge outward. The two events lined up. A piece of the star, weighing perhaps several Earth masses worth of gas, was launched upward at high speed. As this hot gas climbed away from the surface, it cooled, and as it cooled, something remarkable happened. The atoms inside it began to stick together, forming microscopic dust grains, tiny solid specks of carbon, silicon, oxygen, and other elements, trillions upon trillions of them. These dust grains were small, but there were so many of them that together they formed a screen, a curtain of particles thick enough to absorb starlight and redden whatever passed through. From 650 light-years away, that screen looked like a star going dark. Studies published in the years after the event confirmed the picture. Hubble had spotted hot, dense gas moving outward from Betelgeuse's southern hemisphere months before the dimming peaked. The timing matched perfectly. The star really had spit out a piece of itself, and we had watched the aftermath in slow motion. Here is where the story gets uncomfortable. Astronomers know that red supergiants near the end of their lives become unstable. They puff and shed and burp out material at increasing rates as their cores grow hotter and more chaotic. The bigger the burp, the more advanced the star's age. Betelgeuse had just produced one of the largest mass loss events ever observed in real time on a nearby giant. Was it a one-off? Or was it the beginning of a pattern? In 2023, the star did it again on a smaller scale. It brightened beyond anything ever recorded, then faded, then surged. Researchers at Harvard and the Center for Astrophysics began calling these episodes stellar sneezes. The name sounds funny. The reality is not. Each sneeze tells us the star is shedding its outer skin in chunks. Each sneeze means less material holding the star together. Each sneeze brings the deeper, hotter, more dangerous layers closer to the surface, where we can see them. The dust eventually drifted away. The star recovered its brightness. To the casual observer, Betelgeuse was back to normal. But underneath, something new had been seen for the first time. Something tucked inside the star's atmosphere. Something circling. For nearly 100 years, astronomers had a hunch they could not prove. Betelgeuse pulsed in two clear rhythms. One was a roughly 400-day cycle, easy to explain by the star pulsing in and out like a slow lung. The other was much stranger. Every 2,100 days, almost 6 full years, Betelgeuse went through a deeper, longer rise and fall in brightness. Nothing inside a single star seemed to fit a 6-year clock. The simplest explanation was that Betelgeuse wasn't alone. If a smaller star were orbiting close, ploughing through the thin outer atmosphere of the giant, it could push dust around as it travelled. Sometimes the dust would clump in front of our line of sight. Sometimes it would clear out. The brightness we saw on Earth would rise and fall on the timing of that hidden orbit. A 6-year orbit would explain the 6-year cycle perfectly. The problem was that nobody could see this companion. Astronomers tried. They aimed the Hubble Space Telescope at Betelgeuse. They aimed the Chandra X-ray Observatory at it. They tried instrument after instrument. Every time, they came up empty. Whatever was hiding inside Betelgeuse's glow was buried in light 1,000 times brighter than itself. Imagine trying to spot a candle held an inch from a stadium floodlight, from across a football field. That was the problem. Then came July of 2025. A team led by Steve Howell, a senior research scientist at NASA's Ames Research Center, finally cracked it. They used a special instrument called the Ala-Pike Speckle Imager. The name comes from the Hawaiian word for fox, because the instrument is fast and clever. It sits on the Gemini North Telescope, perched on the summit of Mauna Kea in Hawaii. Speckle imaging works in a way most cameras don't. Normal photographs of stars are blurred by the wobbling air above the telescope. Ala-Pike takes thousands of pictures, each one shorter than a heartbeat. Each picture freezes the air's wobble for an instant. Then a computer combines all the pictures and removes the blur, producing an image that looks like it was taken from space. When Howell's team applied this trick to Betelgeuse, something appeared. A tiny point of light, right next to the giant, inside what would have been the giant's outer atmosphere if Betelgeuse was sitting in our solar system. The hidden companion was real. Researchers proposed naming it Siwaha, an Arabic word meaning her bracelet. The name plays on the older Arabic name for Betelgeuse, which connects to the hand of Orion. The bracelet circles the wrist. The bracelet had been there all along. The official recognition of the name came in September 2025. Siwaha is roughly 1.5 times the mass of our Sun. It glows with a hot blue-white light, the colour of a young main-sequence star. Side by side with Betelgeuse, the giant outshines the companion by a factor of around 250. That's why no telescope had ever caught it before. Siwaha is the candle next to the floodlight. A second study led by Andrea Dupree at the Centre for Astrophysics found something even more striking. By tracing decades of brightness data, her team detected a wake of disturbed gas trailing through Betelgeuse's atmosphere, like the wake behind a boat moving across a pond. Siwaha wasn't just orbiting the giant, it was carving through it, and the giant had no idea what was coming. How do you photograph something that has been invisible for a century? You outwit the atmosphere. When you look up at a star and notice it twinkling, you're seeing a problem astronomers have fought for hundreds of years. The atmosphere above your head is a thick, restless fluid. Layers of warm and cold air shift constantly. Light from a distant star passes through dozens of these layers before it reaches a telescope mirror. Each layer bends the light a tiny bit. The result is a wobbling, shimmering image that smears any fine detail into a blur. For decades, the only way to escape that blur was to leave the atmosphere entirely. That's why Hubble was launched into space. From orbit, with no air in the way, Hubble could see fine details no ground telescope could match. But Hubble has limits. It's not always available. It can't be aimed at every target. And even Hubble had failed to find Betelgeuse's companion. Speckle imaging is a clever trick to fight the atmosphere from the ground. Here's the idea. The atmosphere wobbles, but it doesn't wobble instantly. Each pocket of disturbed air takes about 1/50th of a second to shift. If you could take a photograph faster than that, faster than the air can blur the light, you would catch a frozen moment. The image would still be slightly distorted, but it wouldn't be smeared. That's exactly what Alapike does. The instrument captures thousands of extremely short exposures of its target. Then computer software analyzes the speckles, the bright spots inside each frozen frame, and combines them into a single sharp image. The atmospheric blur is essentially erased. Mounted on the Gemini North telescope at the top of Mauna Kea in Hawaii, Alapike had access to one of the steadiest patches of sky on Earth. The mountain rises high enough that telescopes there sit above much of the lower atmosphere. The thin, dry air above Mauna Kea is famously clean for astronomy. When Howell's team pointed Alapike at Betelgeuse, they were betting on this combination. Steady mountain air, thousands of fast exposures, powerful processing. They hoped that, somewhere in the digital pile, a speck of light too faint and too close to be seen by Hubble would emerge from the giant's glare. It worked. In the processed images, Betelgeuse appeared as expected, an enormous bright disk at the centre. But just beside it, well within what would have been the star's puffy outer atmosphere, a faint companion popped into view. The team double-checked, triple-checked, and ran the analysis multiple ways. The light source was real. It moved with Betelgeuse across the sky, meaning it shared the giant's distance from Earth. It was orbiting. The discovery had quiet, almost gentle beginnings, with grainy images and patient computer work, but its meaning struck astronomers like a hammer. For the first time in history, humans had directly imaged a companion star buried inside the atmosphere of another star. This was no ordinary binary system. Most pairs of stars sit comfortably apart, often farther than the planets in our solar system. Siwaha sits inside Betelgeuse's outermost layers, where temperatures, gas densities, and shock waves create one of the strangest environments imaginable. The discovery also opened a door. If Alapike could find Siwaha, what other red supergents were hiding partners? Suddenly, decades of mysterious brightness cycles in stars across the sky had a possible new explanation. But for Betelgeuse, the question was now sharper than ever. What does a hidden companion do to a dying giant? The answer involved gravity, dust, and something far more violent. Long before Siwaha had a name, astronomers were puzzled by a clock they could not find. If you watch Betelgeuse closely for many years, you'll notice it doesn't pulse in just one rhythm. It pulses in several. The shortest is around 185 days. Another runs for 230 days. A larger one beats every 420 days. These cycles are ordinary for a red supergiant. They come from the star expanding and contracting, a slow heartbeat driven by the way pressure and gravity wrestle inside its layers. But there is one cycle that didn't fit. Every 2,100 days, almost exactly 6 years, Betelgeuse went through a deeper, slower rise and fall. The pattern was clean. The pattern was real. And nothing inside a single red supergent explained it. Imagine a drum that beats 4 times a second, twice a second, and once a second. All those rhythms make sense if they come from one drummer. But now imagine a 5th beat that comes once every minute, totally out of step with the others. You'd start to wonder if there were 2 drummers in the room. That's how astronomers felt about Betelgeuse for years. In 2024, 2 separate research papers studied historical brightness data going back over a century. Records from amateur astronomers, professional observatories, photographic plates, and modern digital sensors were all stitched together. Both papers reached the same conclusion. The 6-year cycle could be explained beautifully if a smaller, hotter companion star orbited Betelgeuse with a 6-year period. The companion would not be visible directly, but as it travelled its long orbit, it would push dust around inside Betelgeuse's outer atmosphere. Sometimes that dust would clump along our line of sight, dimming the giant slightly. Sometimes it would clear away, brightening the giant. The result, seen from Earth 650 light-years away, would look exactly like a slow, deep 6-year pulse. The papers were a strong case made from indirect evidence. The smoking gun, an actual image of the companion, came the following year with Alapeke. Once Sawaha was confirmed, the picture clicked into place. Sawaha takes about 2,100 days to complete one orbit around Betelgeuse. As it loops around the giant, it passes through different regions of its puffed-up atmosphere. On one side of the orbit it pushes dust toward us, on the other side it shoves dust away. The brightness we measure rises and falls in time with its journey. In short, Betelgeuse's mysterious heartbeat wasn't really Betelgeuse's. It belonged to its hidden partner. This finding doesn't only solve a riddle, it changes what we think Betelgeuse is doing right now. Some astronomers had argued the 6-year cycle came from inside Betelgeuse itself, perhaps from something deep in its structure as it neared the end of its life. If that were true, the giant might be in an advanced evolutionary phase, ready to explode within only a few decades to a few centuries. But if the 6-year cycle is just Sawaha's orbit, then that argument loses its power. Without that signal, the evidence for an extremely close supernova weakens. Some models suggest Betelgeuse might still have hundreds of thousands of years left. So the discovery cuts both ways. It explains the strange brightness pattern. It also pushes the supernova timeline farther into the fog. The truth is, scientists are no longer certain whether Betelgeuse will explode in our lifetimes or in the deep future. But there is another scenario, and it's far stranger than either option. Ask 10 astronomers when Betelgeuse will explode, and you'll get 10 answers. The honest range is enormous. Some serious models say tens of years, others say tens of thousands. The most quoted figure is somewhere around 100,000 years, with a wide error bar in either direction. Compared to a human lifetime, that range is meaningless. Compared to a star's lifetime, it's a tight prediction. Why such a huge spread? Because we cannot see inside the star. Telescopes show us only the surface, the outermost layer of plasma we call the photosphere. Below that surface, hundreds of thousands of miles deep, the core does its real work. The core is where the fate of the star is decided. The core is where the timer is running. And the core is hidden. Stars run on a kind of nuclear ladder. They start by fusing hydrogen into helium, the simplest reaction. When the hydrogen runs out, they switch to fusing helium into carbon. Then carbon into neon. Then neon into oxygen. Then oxygen into silicon. Then silicon into iron. Each step is faster than the one before. Each step burns hotter and more violently. The first stage, hydrogen burning, takes most of a massive star's life. For Betelgeuse, That phase lasted around 8 or 9 million years. Helium burning took perhaps another million. Carbon burning lasts only about 1,000 years. Neon burning lasts about a year. Oxygen burning lasts a few months. Silicon burning lasts only days. After that, the core can hold itself up no longer. So when scientists try to figure out Betelgeuse's timeline, they are really trying to figure out which rung of the ladder it's currently on. A team led by Dr. Hideyuki Sayo at Tohoku University analysed Betelgeuse's pulsations and concluded that the star is in the late stage of core carbon burning. If that's correct, then the star has perhaps a few decades to a few centuries before its core collapses. That would mean a real chance of seeing the explosion in our lifetime, or at least our grandchildren's. Other teams disagree. A group led by Lilsol Molnar at Konkoly Observatory in Hungary places Betelgeuse in an earlier helium burning stage. If they're right, the star has hundreds of thousands of years left before its grand finale. The discovery of Siwaha complicated everything. Some pulsation models depend on the long 6-year brightness cycle. If that cycle isn't from Betelgeuse but from its companion, then certain age estimates have to be redone. Some estimates that previously suggested an imminent supernova become weaker. Other estimates remain intact. There's another twist. Even if Betelgeuse hasn't exploded yet from our point of view, it may already be dead in reality. Light takes 650 years to travel from Betelgeuse to Earth. So when you look up tonight, you're seeing the star as it was around the year 1375. Anything that has happened to it since then is invisible to us. If Betelgeuse exploded in 1400, the flash is more than 200 years away from reaching us. We won't know until the light arrives. Right now, a wave of photons might be racing through interstellar space, carrying news of an explosion that already happened. We can't see the wave. We can't detect it ahead of time. We can only wait. That waiting, though, isn't passive, because as the timer ticks down, something else is happening inside the star itself. The interior of Betelgeuse is a layered furnace. Picture an onion the size of half our solar system. At the very heart, in a region maybe a few thousand miles across, sits a tiny, blistering core where the temperature climbs above 1 billion degrees Fahrenheit. Around that core, layer after layer of fusion reactions burn at lower temperatures. Each layer is pushing outward with thermal pressure, while the entire mass of the star above tries to collapse it inward with gravity. Right now, in Betelgeuse's heart, carbon is most likely the fuel. Carbon burning is the third major rung on the fusion ladder. It begins when the temperature in the core hits roughly 1 billion degrees and the pressure becomes crushing. At that point, carbon nuclei smash into each other so hard they fuse into heavier elements like neon, sodium, oxygen, and magnesium. Each collision releases energy. That energy keeps the star from collapsing under its own enormous weight. Carbon burning sounds dramatic, and it is. But the truly terrifying part is how quickly it ends. A massive star of around 17 to 20 solar masses can spend millions of years burning hydrogen. It might spend hundreds of thousands of years burning helium. But carbon burning lasts only about 1,000 years. 1,000 years to use up all the carbon in a region many times more massive than our Sun. 1,000 years sounds like a long time. To the universe, it's a blink. If Sayo's analysis of Betelgeuse's pulsations is right, the star is not just in carbon burning, it's near the end of carbon burning. And what comes after is shorter and shorter and shorter. After carbon comes neon. Neon burning lasts about a year. After neon comes oxygen. Oxygen burning lasts a few months. After oxygen comes silicon. Silicon burning lasts a few days. A few days. From silicon ignition to core collapse, there's almost no warning at all. Picture this from the star's outer layers. The puffed up surface, the convection cells, the dust clouds being thrown off the surface, none of these have any idea what's happening deep inside. The core can switch fuels and pressures and temperatures, and the surface only sees subtle vibrations days or weeks later. That's part of why predicting the explosion is so hard. The visible signs lag far behind the hidden cause. Each fusion stage produces ash that becomes the next stage's fuel. Carbon ash is neon and oxygen. Neon ash is more oxygen and magnesium. Oxygen ash is silicon and sulfur. Silicon ash is iron. Iron is the wall. Iron is the element where this entire process ends. Once a star's core fills with iron, fusion can no longer release energy. The star's furnace, which has held it up for millions of years, suddenly stops working. The pressure that fought gravity is gone in an instant. Everything above that core has nothing left to support it. The collapse takes less than 1 second. That's the hidden countdown ticking inside Betelgeuse right now. Maybe 1,000 years left of carbon burning. Maybe just a few. Maybe almost none. From outside, we cannot tell. From outside, the star looks like a slowly pulsing red giant. From inside, it might be running out of carbon as you read this, and the fuse, once carbon is gone, becomes shockingly short. Everything you have ever touched was forged inside a dying star. The carbon in your bones, the oxygen in your blood, the iron in the wires of the device near you right now. Every one of those atoms came from the same kind of process happening inside Betelgeuse, this very moment. Stars are universal factories. They build the periodic table one rung at a time. The fusion ladder begins gently. A young star like our Sun fuses hydrogen, the simplest atom in nature. 4 hydrogen nuclei smash together and form one helium nucleus. The mass difference between the 4 hydrogens and the 1 helium gets converted directly into energy. That energy heats the star, lights its surface, and warms planets like ours from afar. Hydrogen burning is the long, slow phase that defines most of a star's life. When hydrogen runs out, the core squeezes inward. The squeeze raises the temperature. At high enough temperatures, helium itself becomes fuel. 3 helium nuclei fuse to form 1 carbon nucleus. This is called the triple alpha process, and it sounds calm enough. But helium burning is far hotter and shorter than hydrogen burning. For Betelgeuse, helium burning probably lasted a few 100,000 years. After helium comes the strange and short-lived stages. Carbon burning ignites at around 1 billion degrees Fahrenheit. 2 carbon nuclei collide and fuse, producing neon, sodium, magnesium and oxygen. This is where Betelgeuse most likely sits today. Carbon burning lasts only about 1,000 years. When carbon runs out, the core squeezes harder. Temperatures climb past 1.5 billion degrees Fahrenheit. Now neon itself can fuse. The reactions produce oxygen and magnesium. Neon burning lasts about a year. Then oxygen burning takes over at around 3 billion degrees. Oxygen fuses into silicon, sulfur, phosphorus and other heavy elements. This phase lasts only a few months. Then silicon burning at temperatures above 5 billion degrees. Silicon fuses into nickel and a chain of other elements. The end of this chain is iron. Silicon burning lasts only days. Notice the pattern. Each stage is hotter than the last. Each stage is shorter than the last. The reason is buried in physics. Higher temperatures mean faster reaction rates. Faster reactions mean fuel burns through quickly, and each new fuel produces less energy per gram than the one before, so the star has to burn more of it just to stay supported against gravity. By the time a star reaches silicon burning, the core is producing energy at a furious pace. But every gram of silicon converted into iron releases barely any energy at all. The star is running out of profit. The fusion engine is sputtering. Then comes iron. And iron is the wall that ends everything. Betelgeuse, like every massive star before it, is climbing this ladder right now. Each rung gets it closer to a moment that will release more energy in a single second than our Sun will produce in its entire 10 billion year life. The ladder is also why we are here at all. The carbon, oxygen, calcium and iron in your body were forged in stars exactly like Betelgeuse. When those stars exploded, they scattered their fresh atoms into space. Those atoms eventually formed planets and people. Every supernova is a death. Every supernova is also a birth. The next stage of Betelgeuse's life is the rung where everything stops working at once. Iron is the moment a massive star runs out of options. For its entire life, a star survives by balancing two huge forces: gravity, the constant inward crush of its own enormous weight, and thermal pressure, the outward push of heat from fusion in the core. As long as fusion makes energy, the heat keeps the gas pushed out. As long as the gas stays out, gravity is held at bay. But fusion is only profitable up to a point, and that point is iron. Here's why. Every element on the periodic table can be measured for how tightly its protons and neutrons are bound together. If you fuse two light elements, the resulting heavier element is more tightly bound. The leftover energy is released as heat. That heat is what powers the star. Iron sits at the peak of this binding curve. Iron's protons and neutrons are packed about as efficiently as nature allows. To fuse iron into anything heavier, you don't get energy out. You have to put energy in. For a star, this is a catastrophe. When silicon burning ends, the core fills with iron, layer upon layer of iron, growing every second as silicon ash piles on. The core gets hotter and denser. The star on the outside doesn't know any of this. The surface looks the same. The dust shells look the same. From 650 light years away, an observer with a telescope would see nothing unusual. But inside, the iron core grows. Once that iron core reaches a critical mass, called the Chandrasekhar limit, around 1 4/10 times the mass of our Sun, gravity overwhelms every force that has been, holding it up. The core can't fuse to make energy. The core can't push back. The core has nothing left. What happens next is hard to picture. The iron core, originally about the size of Earth, collapses inward at speeds approaching 1/4 the speed of light. The whole structure falls in on itself in less than 1 second. Billions of miles of overlying star suddenly have nothing supporting them from below. They begin to fall too. Inside the collapsing core, temperatures and densities surge to numbers that don't fit easily into ordinary words. Atoms are crushed so tightly that electrons are forced into protons. The two combine to form neutrons. Almost the entire core, in a fraction of a second, becomes one giant ball of neutrons packed so tight that a single sugar cube of the material would weigh as much as a mountain. On Earth. Then the neutrons hit a wall of their own. They cannot be packed any tighter. The collapse halts in an instant. The infalling material crashes into this newly formed neutron core like a freight train hitting a brick wall. The result is a rebound, a shockwave, a flood of particles called neutrinos blasting outward from the collapsed core. Together, they tear the rest of the star apart. A Type II supernova has begun. For Betelgeuse, this entire sequence, from silicon running out to the shock blowing out the surface, will take only a few hours. A few hours after 1,000,000 years of life. And here on Earth, 650 light years away, we will receive the first warning of this catastrophe in a way that almost no one expects. Not light, not heat, something almost untouchable, something that passes through entire planets without slowing down. Sit with this number for a moment. 1 second. That's all it takes. After millions of years of stable burning, after 1,000 years of carbon fusion, after a year of neon, after months of oxygen, after days of silicon, the final act takes 1 second. The iron core, having reached the Chandrasekhar limit, suddenly cannot support itself. Imagine you're holding a bowling ball above your head. Your arms are tired. They've been holding it for a long time. Your muscles finally give out. The ball drops. That's roughly what happens to the iron core, except the bowling ball weighs more than the sun, and your arms are the very fabric of nuclear pressure. When that pressure fails, the core falls, and it doesn't fall slowly. Material at the edge of the collapsing core accelerates inward at speeds reaching 70,000 kilometers per second, around 43,000 miles per second, almost a quarter the speed of light. The core, which had been roughly the size of Earth, shrinks down to the size of a small city in milliseconds. Then it shrinks further into a ball maybe a dozen miles across. The density at this point is staggering. A teaspoon of the core material would weigh around 1 billion tons. At these conditions, the rules change. Electrons, which normally orbit atomic nuclei, are pressed so hard they actually merge with protons. Each electron and proton fuse into a neutron. The merging releases a particle called a neutrino. Just one of these mergers makes one neutrino, but the entire core merges at once. The number of neutrinos released defies imagination. In the first 10 seconds of the collapse, the dying core spits out around 10 to the 57th neutrinos. That's a 1 followed by 57 zeros. To put that in scale, that single burst of neutrinos carries away about 99% of the total energy released by the entire supernova event. Only about 1% of the energy goes into light, motion, and the spectacular explosion you'll see in the sky. Most of the violence is invisible. The collapse halts when the neutrons can't be squeezed any tighter. There's a quantum mechanical pressure called neutron degeneracy pressure that finally pushes back. The infalling outer layers of the core, racing inward at near light speed, slam into this newly hardened neutron ball and bounce. A shockwave forms. It races outward through the rest of the star. By itself, that shockwave might stall. The matter falling in is so dense and the energy so wild that the bounce alone might not be enough to blow the star apart. What rescues the explosion is the neutrino flood. Even though neutrinos almost never interact with matter, here the densities are so insanely high that even a tiny fraction of those neutrinos deposit their energy into the surrounding gas. They reignite the stalled shockwave and push it outward with renewed fury. The shock starts deep inside the star. It then travels outward through layer after layer of the onion structure: silicon, oxygen, neon, carbon, helium, and finally hydrogen. It takes hours to climb through Betelgeuse, because Betelgeuse is so vast. The star is so big that even a shockwave moving at thousands of miles per second needs hours just to reach the surface. The outside of Betelgeuse, all the while, looks normal. The dust, the puffy atmosphere. Siwaha quietly orbiting nearby. None of them know yet. Then the shockwave breaks out, and the universe lights up. Hours before any human eye sees Betelgeuse explode, a flood will already have passed through us. When the iron core collapses, the burst of neutrinos races outward at almost the speed of light. These ghostly particles barely interact with anything. They stream straight through the entire collapsing star without slowing down. The star's outer layers, still oblivious, are dense with gas and dust. But the neutrinos slip past as if the star were transparent. At the same moment, the rebound shockwave is just starting to climb outward. It moves fast by ordinary standards, but compared to nearly light-speed neutrinos, it's slow. The shock takes hours to reach Betelgeuse's surface. So the neutrinos win the race. For about 3 hours, while the shockwave is still grinding its way through the inner layers of the star, the neutrinos are already crossing 650 light-years of empty space toward Earth. Then they arrive, trillions upon trillions of them. They flow through the planet in a few seconds, passing through buildings, oceans, mountains, and bodies as if none of those things existed. You would not feel a thing. You would not see a thing. Neutrinos are so weakly interacting that almost all of them sail through Earth without ever colliding with a single atom inside it. Standard estimates suggest that during a supernova at this distance, only a small fraction of 1% of the neutrinos passing through your body would interact with you in. Anyway, the dose would be harmless, but specially built detectors deep underground would scream. Around the world, neutrino observatories sit waiting. Super Kamiokande, buried beneath a mountain in Japan, holds 50,000 tons of ultra-pure water. Ice Cube, embedded inside a cubic kilometre of Antarctic ice, watches for the same particles. There are smaller detectors in Italy, Canada, China, and elsewhere. All of them are connected by an alert system called SNEWS, the Supernova Early Warning System. When a wave of neutrinos from Betelgeuse arrives, the detectors will register a sharp spike in just seconds. Computers will compare timing data from multiple sites. Within minutes, an automatic alert will fire to astronomers everywhere. Hours of warning will be granted before any visible flash appears in the sky. This warning is precious. Astronomers will be able to pre-aim their telescopes. They'll be ready to capture the first photons of the explosion the very second they reach Earth. We've never had that kind of preparation for a nearby supernova in human history. The neutrino flood from a Betelgeuse supernova would be the most intense neutrino signal ever recorded. Existing detectors would register hundreds of thousands of events. Some smaller detectors would see more interactions in 20 seconds than they normally see in their entire lifetime. Scientists would suddenly have a high-resolution probe of the inner workings of a collapsing core, something physics has never been able to study directly. For everyone else, the neutrino burst would pass without notice. You'd be drinking coffee, sitting in traffic, sleeping. Trillions of particles from a dying star would race through your body in less than a heartbeat. None would harm you. Then, hours later, the sky would change. The shock wave, after grinding through hours of stellar material, would finally reach Betelgeuse's surface. The outer layers of the star would erupt outward at thousands of miles per second. A burst of light would race toward Earth, taking the same 650 years the neutrinos took, but arriving hours behind because of the time it took the shock to reach. The surface. When that light arrived, every human alive would see it. For hours after the core has collapsed, Betelgeuse looks fine. The shock wave is still inside the star. It's punching outward, but Betelgeuse is so huge that even a wave moving at thousands of miles per second has a long road ahead. The wave climbs through silicon ash, then oxygen, then neon, then carbon, then helium. Each layer is heated brutally as the shock sweeps through. Fusion reactions, normally too rare to matter, suddenly fire off everywhere at once. New elements are created in the chaos. Elements heavier than iron, like gold, platinum and uranium, are forged in the crushing wake. While all of this is happening inside, the outer surface, the photosphere we see from Earth, looks unchanged. The convection cells still bubble, the dust shells still drift outward at their leisurely pace. From the outside, nothing seems to be happening at all. Then the shock breaks out. The moment the shockwave reaches the photosphere, the star's surface lights up with a flash of ultraviolet and X-ray radiation. This is called shock breakout, and it lasts only minutes. The brightness during this short pulse rises to phenomenal levels, but its peak comes mostly in wavelengths your eyes can't detect. Then the visible light begins. The outer layers of Betelgeuse, suddenly hit by an enormous heatwave from below, begin to expand. They expand at speeds reaching thousands of miles per second. As they expand, they cool slightly, which actually allows visible light to escape more easily. The star brightens. In the first day, Betelgeuse's brightness leaps. By the end of the first week, it has multiplied by a factor of millions. By 2 weeks, the explosion has reached its peak. At peak, Betelgeuse will shine with the brightness of around 100 million suns. It will pour out more visible light in a few weeks than our sun will produce in its entire 10 billion year life. From Earth, it will look like a tiny star burning so violently it pierces the daytime sky. For the first time in history, humans alive today might watch a star blow up close enough to dominate the night. The peak brightness from Earth is expected to roughly match the full moon. But here is the strange part. Even though the total light is comparable to the moon, all of it will come from a single point of light. The moon spreads its glow across a half-degree disk in the sky. Betelgeuse will not. It will be a pinprick. That makes the light feel sharper, harsher, almost painful to look at directly. For a few weeks, Betelgeuse will be the brightest star anyone alive has ever seen. It will be visible during the day, easily picked out against the blue sky. At night, it will cast shadows. People will walk down streets and notice the strange double lighting of moonlight and supernova light combining to create a softer, eerier glow. After 2 weeks, the star begins to fade. The fade is slow. Over months, the brightness drifts downward. Even after 100 days, it will still be visible during daytime. After 6 months to a year, you'd still spot it easily at night with the naked eye. After 2 years, it would still be visible, though dim. Then, some years later, Betelgeuse would vanish from human sight forever. Orion's red shoulder would be gone, but the death of one star sets a longer story in motion, one that won't finish for tens of thousands of years. Imagine a clear afternoon, blue sky overhead, sun shining as it always does, and then, near the constellation Orion, a second point of light. Not as big as the sun, not as warm as the sun, but unmistakable. A bright, hard pinpoint of light, visible against the daylight blue, casting almost no heat but pouring out an unsettling amount of light. That is what Betelgeuse going supernova will look like from Earth. For about 2 weeks after the peak, Betelgeuse will rival the Moon in total brightness, but because all that light comes from a single point, rather than spread across a disk, the experience is harder to predict. People who look at a full moon at night don't squint or look away. The light is gentle. A point source as bright as the moon would be far harsher. Looking directly at Betelgeuse at peak would be uncomfortable, possibly even painful, like staring at a welder's flash from a great distance. During the day, the supernova would punch through the blue sky. You could spot it by walking outside and looking toward where Orion sits, even though the rest of the constellation would be invisible against the daylight. Betelgeuse alone would shine through. In some sense, Earth would briefly have a second sun, although a much, much fainter one. At night, the effect would be stranger. Most stars in the night sky are tiny bright dots. Even the brightest, like Sirius, are barely noticed by people who don't pay attention to the sky. Betelgeuse during the supernova would change that completely. It would dominate the darkness. Streetlights would feel weaker by comparison. Shadows would stretch from this new point source, the way shadows fall from a flashlight in a dark room. Animals might notice it. Migratory birds use stars to navigate. Insects respond to changes in light. Some species would adjust their behaviour, sometimes in confusing ways. Researchers would suddenly have a chance to study how natural systems respond to a sudden, prolonged change in night brightness. For human cultures, the moment would be unforgettable. Throughout history, people have written about supernovae they saw in the sky, even when those events were much fainter than what Betelgeuse will deliver. In the year 1054, Chinese astronomers recorded a supernova so bright it was visible during the day for nearly a month. The remnant of that event, the Crab Nebula, is still studied today. That supernova was thousands of light years away. Betelgeuse is much, much closer. What it will look like to us is a brightness no living human has ever experienced. Old paintings and folktales mention guest stars, sudden bright additions to the night sky, but those records were written by people who didn't have aeroplanes, the internet, or live television. Betelgeuse's moment, when it comes, will be the most documented event in the history of astronomy. Every smartphone, every observatory, every telescope on Earth and in orbit will be turned toward it. Photographs will be everywhere. Within hours, every news source on the planet will run stories about the bright new dot. Religious leaders, scientists, conspiracy theorists, school children and military officers will all weigh in. Then, slowly, the dot will dim. Over weeks, over months, over years. For all our fascination, though, we should be honest about something else. From this far away, Betelgeuse cannot harm us, but let's see what's actually going to reach Earth, and why distance is the only thing that matters. Try to picture how big Betelgeuse really is. You can't. Almost no one can. Take our Sun. Our Sun is a ball of plasma roughly 860,000 miles across. That number is so far beyond human scale that it stops feeling real. Earth's diameter is about 7,900 miles. The Sun is about 109 times wider than Earth. Already your imagination is starting to fail. Now multiply that by 700. Betelgeuse's radius is estimated at somewhere between 640 and 760, 4 times the radius of our Sun. The star is so swollen, so puffy, that its outer atmosphere drifts and shifts in ways even astronomers struggle to define. It doesn't have a sharp surface like Earth, or even a clean edge like our own Sun. The edge of Betelgeuse is more like the edge of a fog bank. To make it real, here is the comparison that shocks people the most. If you took our Sun out of the centre of our solar system and dropped Betelgeuse in its place, what would happen? Mercury would not exist. The planet would be deep inside Betelgeuse, somewhere around the middle of the star's interior. Venus would be gone, buried in stellar plasma. Earth would be gone, vaporized inside the star's outer layers, somewhere near the middle of the boiling photosphere. Mars would be gone. Its orbit would lie inside Betelgeuse, surrounded by red glowing gas at temperatures of thousands of degrees. The asteroid belt would mostly be inside the star. Jupiter, the giant of our solar system, would skim along the very outer edge of Betelgeuse's atmosphere. Some estimates place the star's outer reaches a little past Jupiter's orbit. Some place them just before. Either way, the largest planet in our solar system would be at the boundary of this single monstrous star. Saturn and beyond would be safely outside, watching the spectacle. Stop and let that picture form. Our entire inner solar system, the place where every planet we can land probes on currently lives, would be erased and replaced by a single roiling ball of plasma. This size has consequences. A star this huge, this bloated, this loosely held together, can't last. The very thing that makes Betelgeuse impressive also makes it fragile. Material at the surface is weakly bound to the rest of the star. Convection cells are so massive they can launch chunks of material thousands of miles outward. Gravity at the surface is a fraction of what it is on smaller stars, so dust and gas escape into space all the time. In fact, Betelgeuse loses about 1/1,000,000th of a solar mass every year. That sounds small, but over time that adds up. Some estimates suggest Betelgeuse has shed several Earth masses of material into space over the last 100,000 years. The dust, gas and debris from that loss form a faint, complicated nebula around the star, currently invisible to the naked eye but visible to powerful infrared telescopes. There's a lesson in this size. Big stars don't just live shorter lives, they live louder lives. They throw off more material. They burn brighter. They die more violently. And the giant in Orion's shoulder is one of the loudest of them all, growing more chaotic by the year. Look at Betelgeuse with a powerful infrared camera and the picture changes. To your eye, the star looks like a tiny red dot. Through optical telescopes, it shows up as a small disk, sometimes with hints of darker patches on its surface. But infrared telescopes see something else entirely. They see the heat radiated by dust and gas drifting around the star, far beyond the visible photosphere. What they see is messy. Betelgeuse is wrapped in a tangle of streamers, blobs, and shells. Some of these structures sit close to the star within a few hundred star radii. Others stretch out to several thousand star radii. There are arcs of dust looping back toward the star. There are plumes that look like slow-motion explosions frozen in time. There are bow-shaped ridges where the star's outflow runs into the thin gas between stars. Picture a candle on a windy night. The flame flickers. The smoke rises in twisting strands. Now picture that candle is a star, the smoke is hot dust travelling at miles per second, and the wind is the surrounding interstellar medium. That's Betelgeuse. Most of these streamers come from mass loss. Red supergiants are notorious for shedding material. They drop atoms into space the way a tree drops leaves. The process isn't smooth or even. it happens in bursts. A convection cell rises up, throws off a chunk of plasma, and the chunk drifts away. Another cell does the same. Over time, the star surrounds itself with a complex cloud of debris. Recent studies have detected several distinct shells around Betelgeuse. The innermost shell sits within roughly 100 star radii. A larger shell extends to several hundred radii. Beyond that, evidence suggests an even older, more diffuse shell from a previous era of mass loss. These shells are time capsules. Each layer was thrown off when the star was in a different mood. The innermost layer might be only a few thousand years old. The outermost might be tens of thousands of years old. Reading them is like reading tree rings, except instead of revealing a tree's growth, they reveal a star's slow unravelling. Recent research using the Atacama Large Millimeter Array, called ALMA, has imaged the surface of Betelgeuse and traced the gas just above it. The images show enormous bubbles of plasma rising from the surface, then collapsing back, then rising again. Some of these bubbles are wider than the orbit of Earth, the rising and falling churn material mixing it, then occasionally throwing it free. The 2019 dust plume that caused the Great Dimming likely came from one of these big convective surges. The plume rose, cooled, condensed into dust, and floated away. It joined the larger family of debris already surrounding the star. There is something else worth noting about all of this. As Betelgeuse approaches its eventual supernova, the rate of mass loss is expected to grow. Some models suggest the final centuries before the explosion involve violent, episodic eruptions that throw off solar masses worth of material. The streamers around Betelgeuse today might be only the early, gentle stages of a process that will get far more dramatic. When the supernova finally goes off, the explosion will slam into all of this surrounding debris. Shockwaves will plough through the streamers and shells. Light will brighten and fade in patterns shaped by the geometry of the surrounding material. Astronomers will get a unique chance to read the star's recent history written into its own death. But all of this is happening while a much smaller object is buried inside, patiently doing its own destructive work. Siwaha is not safe. The companion star discovered in 2025 orbits Betelgeuse at extremely close range, close enough that it sits within the outer atmosphere of the giant. As it travels, it doesn't move through clean empty space. It pushes through warm gas, ploughs through dust, and creates a wake of disturbed material trailing behind it. This is gentle now. It will not stay gentle. Studies led by Andrea Dupree at the Centre for Astrophysics traced Siwaha's effect on Betelgeuse's atmosphere. The companion's gravity pulls and stirs nearby gas. Material flows toward the small star, gets accelerated, and forms long streams. Some of that material rains down onto Siwaha itself. Some of it gets thrown back into Betelgeuse's atmosphere. The interaction is constant. Each pass shaves a little energy off Siwaha's orbit. The friction between the companion and the surrounding gas, plus the tidal forces from Betelgeuse's enormous gravity, slowly drag Siwaha inward. The orbit shrinks. The companion moves a tiny bit closer to the giant with every loop. Estimates suggest that within the next 10,000 years, Siwaha will spiral too close. Tidal forces will overwhelm whatever cohesion the smaller star has. Then, Siwaha will be torn apart and absorbed into Betelgeuse's outer envelope. The merger will be one of the most violent events in the recent history of this stellar system, possibly bigger than any of the dust eruptions seen so far. Material from Siwaha will plunge into Betelgeuse, releasing huge amounts of energy. The giant might brighten dramatically for years, possibly decades. Massive plumes of debris would be launched into space. Some astronomers have even suggested that the merger itself could trigger Betelgeuse's supernova. Adding mass and angular momentum to a star already tottering on the edge of stability could be the final push. A merger with a star of 1.5 solar masses is a significant disruption. Models from the Betelgeuse project, a research effort led by Craig Wheeler at the University of Texas at Austin, suggest that mergers in red supergiants can spin them up, dredge fresh fuel into the core, and accelerate evolution in unexpected ways. Whether or not the merger directly triggers the supernova, it will reshape the star. Betelgeuse after Sawaha would look different from Betelgeuse before. The atmosphere would be more extended, more chaotic, more loaded with debris. The convection patterns would shift, the mass loss rate would jump. There's another angle to this dance. Right now, in November of 2027, Sawaha is expected to reach what astronomers call greatest elongation. That's the point in its orbit where it sits as far from Betelgeuse, as seen from Earth, as it can get. At greatest elongation, the companion is most easily detectable from our point of view. The next chance to study Sawaha closely will be that 2027 window. Telescopes around the world are being prepared for that observation campaign. What astronomers learn during that window will shape predictions for everything to come. A more accurate orbit, a better mass measurement, a clearer picture of how Sawaha interacts with Betelgeuse's atmosphere. Each measurement narrows the timeline for the merger. Each measurement narrows the timeline for the supernova. In the meantime, Sawaha and Betelgeuse continue their slow, deadly waltz. The smaller star burns through one of the strangest environments any star has ever inhabited. The giant slowly digests its partner. And 650 light-years away, scientists watch with the kind of patience that only astronomy can teach. Two stars locked in an embrace, neither can survive. Could Sawaha actually push Betelgeuse over the edge? The idea sounds dramatic, but the physics is real. When a smaller star spirals into a bigger one, the energy released is enormous. The combined mass, momentum, and angular speed of two stars is far more than either could carry alone. Drop all of that into a giant already wobbling near the end of its life, and you have a recipe for genuine disruption. Models from the Betelgeuse Project, a research effort led by J. Craig Wheeler at the University of Texas at Austin, examined exactly this scenario. The team simulated what happens when a red supergent absorbs a companion of around 1 solar mass. The results were striking. The merger spun the giant up. The increased rotation dredged hotter material from the inside up toward the outer layers. Mass loss surged. The star's structure became less stable. In some of the simulations, the absorbed companion's gas mixed deep into the star and altered the energy balance of the core. The fusion reactions changed pace. The fragile balance between gravity and pressure shifted. In a few cases, the stage of the star's life shortened dramatically. If this is what happens to Betelgeuse, the supernova countdown becomes shorter than current estimates suggest. The giant might burn through its remaining fuel faster than predicted. A star that would otherwise last a few 100,000 more years might be reduced to a few thousand. Or fewer. Here is the unsettling part. Astronomers think the merger has happened before. Studies of Betelgeuse's spin rate suggest the star is rotating much faster than expected for an isolated red supergiant. The most natural explanation is that at some point in the past, Betelgeuse already swallowed a companion. That earlier event is what spun it up to its current speed. A second merger, with Sawaha, would just be another swallowing. The shape of the future merger is harder to predict. Some models suggest the smaller star simply gets dissolved into the giant's atmosphere over a period of years, releasing energy slowly. Other models predict a more violent event, with huge mass ejections and a sudden brightening. In a few extreme scenarios, the merger releases enough energy to mimic a small supernova by itself, even before the real one arrives. Then there's the question of what the merger does to the iron timer. If Sawaha's mass is added to Betelgeuse's outer layers, the giant's gravity becomes slightly stronger. The pressure at the core climbs slightly. Fusion runs slightly hotter and faster. The countdown to silicon burning shortens by a tiny fraction. None of these changes are enormous on their own, but Betelgeuse is already at the late stages of its life. Even tiny changes could matter. The merger might also affect the type of supernova. A more massive, faster spinning star might produce a brighter, more asymmetric explosion. The shape of the blast could be lopsided, with one side ejecting more material than the other. The neutron star or black hole left behind might receive a powerful kick, sending it racing through space at hundreds of miles per second. For now, all of this is theory. The real test comes during the November 2027 observation window, when astronomers can study Siwaha's orbit in detail. A precise measurement of the companion's distance, mass, and trajectory will reveal how fast the spiral is happening. From that, scientists can estimate how many thousands of years remain before the smaller star is consumed. What waits at the end of that calculation, no one can say for certain, but the hourglass has been visible for millennia, even if no one knew where to look. Betelgeuse keeps surprising people. In 2023, just a few years after the Great Dimming, the star did the opposite of what it had done before. It got brighter than astronomers had ever recorded. For a brief stretch, Betelgeuse was the brightest star in Orion, outshining even Rigel, the bright blue star at the Hunter's Foot. People who looked up that winter saw a constellation that looked subtly wrong, with the shoulder shining harder than the foot. The brightening events have been happening more often. Each one is small. Each one fades within weeks or months. But the pattern is unusual. Healthy red supergiants pulse. They rise and fall in brightness on regular cycles. What Betelgeuse has been doing lately doesn't always fit those cycles. The brightening surges are layered on top of the normal pulsations, suggesting something extra is happening underneath. Some astronomers believe these surges are signs of increased convection activity, with bigger and more powerful cells rising from deep inside the star and pushing huge amounts of hot plasma to the surface. Other astronomers think the brightenings are connected to mass loss. As Betelgeuse sheds material, gaps occasionally clear in the surrounding dust. When a clear path opens between us and the star's surface, the brightness jumps. When new dust forms or drifts back into the line of sight, the brightness drops. Over time, this leads to a flickering, uneven pattern. A third possibility involves Siwaha. As the companion sweeps through different parts of Betelgeuse's atmosphere, it disturbs gas in different ways. On certain segments of the orbit, it might temporarily clear out dust along our line of sight, allowing more light through. On other segments, it might pile dust toward us. The match between Siwaha's orbital period and the long brightness cycle suggests this is real. Each of these explanations has supporters. The truth is probably some combination of all three. What worries some scientists is the trend. Across the last decade, Betelgeuse has produced both the deepest dimming on record and the brightest brightening on record. The amplitude of its variations is growing. The star is restless. The behaviour reminds astronomers of late-stage stellar evolution, when cores switch fuels and convection patterns reorganise. Whether this restlessness signals an explosion within the next century or simply an active phase that lasts thousands of years is impossible to say. But it adds tension to every new observation. Each dimming event makes people wonder. Each brightening makes people watch more closely. Then there is the cultural dimension. In 2019 and 2020, the Great Dimming made worldwide headlines. People who didn't normally pay attention to astronomy started checking on Betelgeuse. The 2023 brightening did the same thing. The star has become a celebrity. Each new burp triggers articles, social media posts, and fresh waves of speculation. For astronomers, this attention is a double-edged sword. The flood of public interest brings funding and observation time. It also brings overhyped claims and misinterpretations. Researchers find themselves constantly explaining that no, Betelgeuse is not exploding tomorrow, while also acknowledging that yes, something interesting is happening up there. The key truth is simple. We are watching a massive star at the end of its life. We are watching it in real time. We see it shake, breathe, throw off pieces of itself, and dance with a hidden partner. Every instability we record is a window into a process that has been studied in textbooks for decades, but never seen this closely. The window will eventually close. But the act of watching is reshaping how we measure cosmic distance, and how late we already are. Look up at Betelgeuse tonight. The light reaching your eye left the star around the year 1375. That is the brutal truth of cosmic distance. Light, the fastest thing in the universe, still takes time to cross space. 650 light years means 650 years of travel time. Whatever Betelgeuse is doing right now, in the actual present, we won't see for over 6 centuries. This creates an uncomfortable possibility. Betelgeuse may already have exploded. It could have happened a century ago. It could have happened 500 years ago. The flash of light from that explosion could be racing toward Earth at this very moment, slicing through interstellar dust and gas, getting closer year by year. We would have no warning. We would simply look up one night, or one day, and find a new bright dot in the sky. How likely is this? Honestly, low. Statistical models that include everything astronomers know about Betelgeuse's mass, evolution, and interior structure place the most likely explosion date somewhere in the next 100,000 years. The chance that the star has already exploded, but the light hasn't reached us yet, is small. But it's not zero. If Betelgeuse exploded just 1 year before the light reaches us, we might detect a few unusual signs in advance, like a slight uptick in cosmic ray intensity or a faint change in the star's brightness profile. But by then, the explosion would already be almost upon us. A more interesting question is what we'd notice if it exploded 1,000 years from now. By that point, human astronomy will likely be unrecognizable. Telescopes in space, on the moon, possibly on Mars. Instruments capable of detecting subtle changes that would be invisible today. Future astronomers might pick up early warning signs decades or centuries in advance, watching the star slowly increase its mass loss, its silicon burning lighting up the outer, layers in faint but detectable patterns. For us, in the present, the wait is more passive. We monitor. We measure. We watch for sudden neutrino bursts that would precede the visible flash. SNEWS, the supernova early warning system, is set up exactly for this. If Betelgeuse goes off in our lifetime, we will probably get a few hours of warning from neutrino detectors before the light arrives. There is something poetic about this whole situation. Stars look eternal. They've been there since the dawn of human history. Cultures across the planet built mythologies around them. The hunter Orion has been recognized in the sky for thousands of years. Babylonians, Greeks, Egyptians, Native Americans, Polynesian navigators, all of them saw a hunter or a hero in those same stars. For all that time, Betelgeuse has been the shoulder. The shoulder might already be gone, or the shoulder might have hundreds of thousands of years left. We genuinely cannot tell. The combination of distance, the limited information we can extract from a single dot of light, and the messy interior of a dying giant means that prediction is hard. Estimates from different research groups land in completely different ballparks. Some say a few decades, some say a few centuries, some say 100,000 years. What is certain is that the explosion will happen. It is locked in, the physics is settled. The only question is when, and whether we, or our descendants, are awake when the news finally arrives. The light is in the mail. We are simply waiting at the mailbox. When Betelgeuse explodes, the fireworks last weeks. The corpse lasts forever. A Type II supernova does two things at once. It blasts the outer layers of the star into space at thousands of miles per second, and it leaves behind a tiny, dense object at the centre, the compact remnant of the original core. For a star of Betelgeuse's mass, the most likely remnant is a neutron star. Picture an object the size of a small city, maybe 12 to 15 miles across, packed with the mass of the sun and a half. The density is unimaginable. A teaspoon of neutron star material would weigh around 1 billion tons. Drop a marshmallow onto a neutron star, and the impact would release the energy of a nuclear bomb. Atoms as we know them don't exist there. The object is one solid mass of neutrons squeezed together, held up only by quantum mechanical pressure. A newborn neutron star is unspeakably hot, around 100 billion degrees just after formation. It cools rapidly, losing heat through neutrino emission, but stays brutally hot for a long time. It also spins. The original star's rotation, concentrated into a tiny sphere by the collapse, makes the neutron star whirl around dozens or hundreds of times a second. Magnetic fields, similarly concentrated, become trillions of times stronger than anything humans can build. Some neutron stars become pulsars. They sweep beams of radio waves across the sky as they rotate, like cosmic lighthouses. If the beam happens to cross Earth, we detect a pulse every rotation. Pulsars are some of the most accurate clocks in the universe. The neutron star left behind by Betelgeuse might or might not be a pulsar, depending on the orientation of its magnetic poles. Could the remnant instead be a black hole? It's possible, but probably not. Stars heavier than around 25 solar masses are more likely to leave behind black holes. Betelgeuse sits at around 16 to 20 solar masses, making it more likely to leave a neutron star. But the boundary between the two outcomes isn't perfectly sharp. If Betelgeuse falls on the higher end of mass estimates, or if a Siwaha merger pushes it over a critical threshold, a black hole could form instead. Either way, the remnant will be small, dense, and effectively invisible from Earth without specialized telescopes. After the supernova fades, only the most powerful X-ray and radio observatories will be able to study it. Hubble, James Webb, and future telescopes would peer into the wreckage to find a faint point of high-energy emission. That point would be the neutron star or black hole, sitting alone where the giant once shone. Around the remnant, the explosion's debris will form a nebula. Filaments of gas, glowing in shades of red, green, and blue, will expand outward from the centre. The pattern will be similar to the Crab Nebula, the famous remnant of a supernova that exploded in the year 1054. That nebula is still expanding nearly 1,000 years later, with detailed structure visible to backyard telescopes. Betelgeuse's nebula will be even more spectacular. Closer, brighter, more detailed. Future generations of astronomers will study it for centuries. But long before we get to nebulae and pulsars, the explosion creates something else. Something fundamental. Something that connects every star to the periodic table itself. Heavy elements. Gold. Platinum. Silver. Uranium, the most precious atoms in the universe, all forged in the brutal seconds of a supernova. In the first weeks after Betelgeuse explodes, its brightness will be powered by the strangest fuel of all. Radioactive decay. When the supernova shockwave tears through the star's interior, it heats material to extreme temperatures, briefly enabling fusion reactions that don't normally happen in healthy stars. One of the products of this rushed nuclear cooking is an isotope called nickel-56. The shockwave produces large amounts of it, possibly several % of a solar mass. Nickel-56 is not stable. It begins decaying immediately into cobalt-56, with a half-life of about 6 days. Cobalt-56 then decays into iron-56, the stable end product, with a half-life of around 77 days. Each step releases energy, and that energy is what keeps the supernova bright after the initial flash fades. For the first few weeks, the brightness comes mostly from the shockwave's leftover heat. The expanding gas glows brilliantly. Then, as the gas cools and expands, the radioactive decay takes over as the dominant power source. The cobalt and nickel buried inside the wreckage keep producing energy long after the initial blast is done. This is why supernova light curves have a distinctive shape. They peak quickly, fade steeply for a while, then settle into a slower, almost linear decline that follows the half-life of cobalt-56. Astronomers can recognize a Type II supernova just by watching its brightness fade in the right pattern. Beyond nickel-56, the supernova produces a long list of other radioactive isotopes. Iron-60, with a half-life of about 2.5 million years. Manganese-53, with a half-life around 3.5 million years. plutonium-244, with a half-life of about 80 million years. These isotopes spread into space along with the rest of the debris, eventually mixing with interstellar gas and being incorporated into new stars and planets. We can find traces of these isotopes here on Earth. Geological samples from the deep ocean floor contain tiny amounts of iron-60, which couldn't have come from anywhere except a nearby supernova that exploded a few million. Years ago, ice cores from Antarctica contained similar traces. The presence of these isotopes is a kind of fossil record, a chemical fingerprint of ancient explosions in our galactic neighbourhood. When Betelgeuse explodes, it will dump fresh radioactive material into space in our region of the galaxy. Most of it will spread thinly over an enormous volume. A small fraction may eventually reach our solar system millions of years from now, when the expanding remnant has had time to drift across the gulf between stars. The radioactive heart of the explosion also drives some of the most exotic features of the supernova nebula. As the radioactive decays release gamma rays, those gamma rays are absorbed by the surrounding gas. The gas heats up. It glows in unusual colours. The energetic radiation can also ionize atoms, producing distinctive emission lines that astronomers use to map the chemistry of the wreckage. Decades after the supernova, when the immediate brightness has faded, the long-lived isotopes will continue to emit energy. The remnant will glow faintly in X-rays for thousands of years. The slow heat from radioactive decay will keep parts of the gas warm long after they would have otherwise cooled. A supernova is, in this sense, a piece of nuclear chemistry on the largest possible scale. Years of radioactive decay, packaged into a few weeks of brilliance and an afterglow that lasts millennia. But the most stunning chemistry isn't in the decay. It's in what gets created in the first place. Almost every gold ring, every silver coin, every platinum wire on Earth was made inside a dying star. For most of the universe's history, hydrogen and helium dominated the chemical inventory. Lighter elements like carbon, oxygen and silicon were produced inside stars over millions of years of fusion. But the heaviest elements, gold, platinum, lead, uranium, couldn't be produced by ordinary fusion at all. They are too heavy, too complex, too far up the periodic table. Their origin is much more violent. When a massive star like Betelgeuse goes supernova, the conditions inside the explosion become so extreme that ordinary nuclear physics breaks down. Temperatures exceed billions of degrees. Pressures pass anything found anywhere else in the universe. The dense flood of neutrinos and free neutrons available during the collapse and rebound creates a brief window where nuclei can absorb extra neutrons faster than they can decay. This rapid neutron capture, called the R process, builds up heavy elements quickly. Iron nuclei catch neutrons. They become heavier and heavier isotopes of iron. Some of those isotopes are unstable and decay into cobalt, then nickel, then copper, then zinc. Others keep capturing neutrons and become much heavier, eventually reaching elements like silver, gold and platinum. A few even reach uranium and thorium. The amount of heavy elements produced in a single supernova is astonishing. Estimates suggest that a typical supernova creates several Earth masses of gold, plus comparable amounts of platinum, silver, and other precious metals. The numbers are eye-watering. A single explosion produces more gold than humans have mined in our entire history. That gold doesn't sit there. It blows outward with the rest of the explosion's debris, spreading through interstellar space at thousands of miles per second. Over millions of years, it mixes with the gas and dust between stars. New stars and planets form from that enriched material. Some of that material ends up in places where it can be used. Earth itself is a child of supernovae. The gold in jewellery, the silver in electronics, the uranium in power plants, all of it came from explosions that happened long before our solar system was born. Stars like Betelgeuse, exploding throughout the history of our galaxy, seeded the gas cloud that eventually formed the Sun and its planets. We are walking around with bits of dead stars in our pockets and our wedding rings. Betelgeuse's eventual supernova will continue this cycle. Several Earth masses of gold, platinum, and other heavy elements will be flung into space. Most of that material will spread thinly across our part of the galaxy, but tiny fractions of it might, in a few million years, find their way into newly forming stellar systems. Some of the atoms made in Betelgeuse's death might one day sit on a kitchen table in a civilization that hasn't been born yet. There is an idea worth holding here. Every time a star dies violently, the universe gets richer. The periodic table grows more complete. New possibilities for chemistry, biology, and life emerge. The most spectacular explosions in cosmic history are also the most generous events. They take the simple ingredients of the early universe and turn them into the complex ingredients we now take for granted. Astronomers studying recent supernovae have used spectroscopy to confirm the production of these heavy elements. The chemical fingerprints in the light from the explosions match exactly what theory predicts. The story is no longer speculation. We have caught the universe in the act of making gold. When Betelgeuse finally goes, every spectroscope on Earth will capture this same chemistry, but in unprecedented detail. Long after the brightness fades, Betelgeuse's death will leave a permanent monument in the sky. The wreckage of a supernova doesn't disappear. The expanding gas, dust and elements form a structure called a supernova remnant, and these remnants can persist for tens of thousands of years. Over time, they expand outward, slowly cooling and dispersing into the surrounding interstellar medium. The most famous example is the Crab Nebula. In the year 1054, Chinese astronomers recorded a guest star bright enough to be visible during the day for nearly a month. That guest star was a supernova explosion in the constellation Taurus, around 6,500 light-years away. Today, almost 1,000 years later, the wreckage is still visible. It looks like a tangled mess of glowing filaments with a fast spinning pulsar at the centre. Betelgeuse's remnant will be much closer than the Crab Nebula, closer than every other known supernova remnant in the galaxy. The angular size, meaning how big it appears from Earth, will be enormous. We'll be able to study its expansion in real time. Generation after generation of astronomers will watch the wreckage spread. Right after the explosion, the remnant will be small and dense, a fireball of debris expanding from the central neutron star. Within years, it will start to take on a more complex shape. Different elements will move at different speeds. Lighter, hotter material will race outward fastest. Heavier, denser material will lag behind. Magnetic fields will twist the gas into filaments and arcs. Over decades, the remnant will run into the surrounding material that Betelgeuse shed during its lifetime. The collisions with those old shells of dust and gas will create powerful shockwaves. These shocks will heat the material to millions of degrees, making it glow brightly in X-rays and ultraviolet light. Centuries from now, the remnant will be an extended structure visible to even modest telescopes. Filaments of glowing gas. Wisps of hydrogen and oxygen. Bright knots where dense clumps are shredded by the expansion. Inside, the central neutron star or black hole will sit alone, surrounded by a roiling cloud of its former outer layers. The constellation Orion, as humans know it, will be permanently changed. Today, the Hunter has a red shoulder. After Betelgeuse's supernova, there will be no red shoulder. Just empty sky for a few decades, then a slowly growing cloud of glowing debris where the giant once burned. People standing under the night sky 1,000 years from now will look up and see a hazy nebula in the place where the brightest red star used to be. The constellation will still be recognizable. The belt will still be there. Rigel, the bright blue star at the foot, will still shine. The other stars of Orion will still hold their familiar shapes. But the shoulder, that signature splash of colour that has marked the figure for thousands of years, will be gone. New stories will be told. New mythologies, perhaps, will be born to explain the change. Cultures will name the nebula. Schoolchildren in the future will learn that the constellation looked different before, that there used to be a giant red star in the upper left. This is the long legacy of a supernova. Not just the brilliant flash, not just the heavy elements scattered through space. the transformation of a familiar piece of the sky into something new, something visibly different to every human eye that comes after. When the dust settles, there is one more thing the explosion will eventually send our way. The flash of light from Betelgeuse will arrive in 650 years. The neutrinos, just hours before. The cosmic rays will take much longer. Cosmic rays are charged particles, mostly protons, that race through space at extremely high speeds. Supernovae are major producers of them. The shock waves blasting outward from the explosion accelerate particles in the surrounding gas to incredible energies. Some cosmic rays approach the speed of light, others travel at slightly slower speeds with a wide range of energies. But cosmic rays don't travel in straight lines. Charged particles get deflected by magnetic fields. The galaxy is full of magnetic fields, threading through interstellar space in complicated patterns. As cosmic rays move through these fields, they get bounced around, change direction, and follow tangled paths. A particle that starts at Betelgeuse might wander through hundreds or thousands of light years of detours before it ever reaches Earth. The result is that cosmic rays from Betelgeuse won't arrive in a single sharp burst. They'll arrive over thousands of years, gradually, as different particles complete different paths through the magnetic maze of the galaxy. The first ones might begin reaching Earth a few centuries after the visible flash. The bulk would arrive over the next 10,000 years. Some would still be coming 100,000 years later. The amount of cosmic radiation reaching Earth would slightly increase during this period. Slightly is the key word. Earth is already constantly bombarded by cosmic rays from countless supernovae across the galactic past. The local cosmic ray flux from the Milky Way's history is what we live with every day. A new supernova at 650 light-years would add to that background, but it wouldn't dominate it. Estimates suggest that a Betelgeuse supernova would increase the local cosmic ray background by a small but measurable amount, possibly a few tens of % at peak, and only, after a delay of several centuries to thousands of years. The increase wouldn't be dangerous to life, it would be detectable to scientific instruments. It might cause minor changes to atmospheric chemistry, possibly altering the production rates of certain isotopes in the upper atmosphere. Researchers studying ice cores and tree rings would notice the change long after the visible event. Rings of trees laid down thousands of years from now might contain slightly elevated levels of carbon-14, beryllium-10, or other isotopes produced when cosmic rays strike. The atmosphere. Future scientists would identify these rings as the chemical signature of Betelgeuse's death, much the way we identify ancient supernovae today by their isotope traces. For satellites and electronics, the increase could be more relevant. Cosmic rays cause occasional glitches in computer chips and damage to spacecraft electronics. A higher background flux would mean a slightly higher rate of these incidents. Engineering would need to adapt, but the changes would be manageable. For biology, the increase is unlikely to matter much. Earth's atmosphere and magnetic field shield us from most cosmic rays. The shielding doesn't go away just because a nearby supernova has occurred. The slight rise in flux would translate to a slight rise in radiation exposure for people in aeroplanes, astronauts and high-altitude regions. The dose increase would be far below anything that causes health concerns. So, the cosmic rays are a long, slow follow-up to the main event. A whisper of energy that arrives long after the visible spectacle has ended, threading its way through the galaxy on tangled paths. But there is one set of consequences from a nearby supernova that has in the past mattered very much. Let's see how Betelgeuse stacks up. When astronomers think about whether a nearby supernova is dangerous, the first thing they look at is the ozone layer. Earth's atmosphere has a thin band of ozone in the stratosphere, between roughly 10 and 30 miles above the surface. That ozone absorbs ultraviolet light from the sun, particularly the more harmful wavelengths. Without ozone, surface life would face damaging UV radiation that would kill plants, harm animals, and cause widespread mutations. Supernovae, especially nearby ones, can damage the ozone layer. The damage comes from cosmic rays and X-rays. When energetic particles or radiation strike the upper atmosphere, they break apart molecules of nitrogen and oxygen. The fragments react with ozone, destroying it. If enough cosmic rays and high-energy photons hit the atmosphere over a short time, the ozone layer can be significantly reduced for years or even decades. How close does a supernova have to be to cause this kind of damage? Models suggest the threshold is somewhere around 25 to 30 light-years. A Type 2 supernova within that range could deplete a significant fraction of Earth's ozone layer, potentially leading to mass extinctions among surface life. Betelgeuse is 650 light-years away. That's far beyond the danger zone. Most calculations show that the supernova's effect on Earth's ozone layer would be minimal. The cosmic rays arriving from such a distance would be diluted by the inverse square law. By the time the radiation flux reaches our atmosphere, it's spread out over an enormous sphere. The intensity at Earth would be many orders of magnitude weaker than it was at the supernova itself. A study published by Adrian Mellott and Brian Thomas examined exactly these scenarios. Their work showed that a Type 2 supernova would need to be roughly 30 light-years or closer to cause significant atmospheric harm. Beyond about 50 light-years, effects become negligible. Beyond 100 light-years, they become essentially undetectable except by very sensitive scientific instruments. Betelgeuse is more than 10 times farther than that critical distance. The supernova will be a magnificent show, but it will not damage the ozone layer enough to threaten life. It will not damage it dangerously, but the radiation that does reach Earth will leave subtle traces. Atmospheric chemistry will shift in tiny ways. Production rates of certain isotopes will change slightly. Future scientists studying ice cores and tree rings will be able to identify the supernova's signature in the chemical record. But the changes will be minor. Nothing about everyday life will be affected. This calmness is reassuring, but it's also the result of luck. If Betelgeuse were closer, the conversation would be very different. There are stars within the danger zone, and a few of them could potentially cause real problems if they go supernova. Betelgeuse just happens to be at a comfortable distance. The danger zone for ozone depletion is one of the reasons astronomers are interested in mapping all the massive stars in our galactic neighbourhood. We want to know where every potential supernova candidate sits. A few stars are within 25 light-years of Earth, but none of them are massive enough to undergo a Type 2 supernova. The closest massive stars are well outside the danger zone. We are safe by the geometry of the galaxy. The next big show is far enough away to be just a show. But there is one specific cosmic threat that some people worry about, and it's worth addressing directly. If you've heard scary stories about supernovae, you've probably heard the phrase gamma-ray burst. A gamma-ray burst is the most violent kind of explosion in the universe. It releases more energy in a few seconds than the sun will produce in its entire life. The radiation is funneled into narrow beams, like a cosmic laser. If Earth happened to be in the path of one of these beams from a nearby star, the consequences could be catastrophic. The atmosphere could be stripped of much of its ozone. Surface life could face severe radiation. Mass extinction would be a real possibility. This sounds terrifying, and people sometimes ask whether Betelgeuse could produce a gamma-ray burst aimed at Earth. The answer is no. Gamma-ray bursts come from a specific kind of stellar collapse, usually involving extremely massive, fast-rotating stars known as Wolf-Rayet stars. These are stars that have shed most of their outer layers, leaving behind a hot, dense core. When such a core collapses, the rotation focuses the explosion's energy into narrow jets along the spin axis. Those jets emit gamma rays in tightly beamed cones. Betelgeuse is not a Wolf-Rayet star. It is a red supergiant, the more relaxed cousin in this stellar family. Red supergiants don't usually have the conditions needed to produce gamma-ray bursts. Their cores rotate too slowly. Their outer layers are too thick. The explosion energy spreads outward in a roughly spherical pattern, not a focused beam. The most famous Wolf-Rayet star considered a potential threat is WR114, located several thousand light-years away. Its rotation axis was once thought to point near Earth, raising concerns. More careful measurements have since shown the axis is angled away, and even if it weren't, The distance is large enough to limit the danger. Other Wolf-Rayet candidates exist, but most are too far to threaten Earth. Betelgeuse, sitting comfortably as a red supergiant, will produce a normal Type II supernova. Brilliant. Spectacular. Visible during the day. But not a gamma-ray burst. No pencil-thin beam of death will be sent in any direction. The energy will spread evenly outward, weakening with distance, harmless by the time it reaches us. Some people online still post warnings claiming Betelgeuse might destroy Earth. These claims tend to mix up gamma-ray bursts with ordinary supernovae, or mix up nearby supernovae with very distant Wolf-Rayet candidates. The reality, established by decades of careful research, is that Betelgeuse's explosion will be safe. A red supergiant of Betelgeuse's mass cannot produce a beamed gamma-ray burst directed at us. It does not have the conditions. The physics simply doesn't allow it. The most dangerous part of Betelgeuse's eventual supernova is, ironically, the brightness. People who look directly at the bright point at peak might experience eye discomfort or temporary visual disturbance. That is the real practical danger. Wear good sunglasses. Don't stare at the spot for too long during the brightest weeks. That's about it. The bigger danger is misunderstanding. Stories about cosmic threats spread fast on the internet. False claims gather attention. Real science gets buried under scary headlines. Betelgeuse's supernova will be the most exciting astronomical event of our possible lifetimes, and it deserves to be appreciated for what it is, not feared for what it isn't. It will be a gift to science. And that gift starts with one of the strangest particles known. A nearby supernova would teach us more about stellar physics than the last 50 years of research combined. Right now, our understanding of how massive stars die comes from a mix of theory, computer simulations, and observations of distant supernovae in other galaxies. Those distant explosions are millions or even billions of light years away. By the time we see them, the events are tiny, unresolved points of light. We can study their brightness curves, we can analyze their spectra. But we can't see fine details. The explosions happen far away, so they look small. Betelgeuse changes all of that. A supernova at 650 light-years would be, by far, the closest we have ever observed. The brightness alone would saturate most existing telescopes. Astronomers would need special filters, new techniques, and entirely new ways of imaging to capture the data without overwhelming their detectors. What we'd learn would be enormous. We could watch the shockwave breakout in real time, with a resolution no distant supernova can offer. We could trace exactly how the explosion expands through Betelgeuse's surrounding shells of dust and gas. The wreckage as it slams into pre-existing material would reveal details about the structure of the star's outer layers in the years and centuries before the explosion. We could measure the neutrino burst with unprecedented precision. The flood of particles arriving in detectors around the world would let us study the very moment of core collapse, the instant when the iron core fails, and the neutron star forms. Decades of theoretical work could be tested directly. Current models predict specific neutrino energies, arrival timings, and total counts. With Betelgeuse, we could see whether reality matches. We could trace the production of heavy elements. Spectroscopy of the expanding wreckage would reveal which isotopes were created, in what amounts, and how they spread. Theories about how gold, platinum, and uranium are forged would be tested with real-time data. Some of the most fundamental questions in nuclear physics could be answered. We could observe the formation of a neutron star or black hole as it happens. The remnant would emerge from the wreckage over months to years. Its early evolution, magnetic field, spin, and radiation patterns would all be studied in detail. Pulsar physics, neutron star structure, and the equation of state of nuclear matter could all be probed in ways previously impossible. And we could watch a supernova remnant grow from infancy. Existing remnants like the Crab Nebula are already centuries old. We see them as adults. Betelgeuse's remnant would let us see a remnant's birth and early childhood, the first years and decades of its existence. The way the wreckage interacts with surrounding material, the formation of filaments and shells, the cooling of hot gas, all of it would be visible. For students, scientists and engineers, the supernova would be a generational event. Careers would be shaped around it. New telescopes might be built to study it. Whole research programs would shift to focus on the wreckage. The amount of new knowledge generated would dwarf the output of any previous astronomical project. Beyond the science, there's something else. The first supernova humans witness up close in the modern age would change how we think about our place in the universe. We would see, in real time, the death of a star and the birth of new physics. We would see proof that stars are not eternal. We would see proof that the universe is alive, changing, dangerous, and full of beauty. The lesson would be both technical and emotional. To capture every second of it, we have a worldwide network already standing watch. When Betelgeuse explodes, we will get hours of warning. Maybe minutes, maybe more. The warning will come from a global network called SNEWS, the Supernova Early Warning System. SNEWS connects neutrino detectors around the world, including Super Kamiokande in Japan, IceCube in Antarctica, Camland also in Japan, Borexino in Italy, and others. When a supernova occurs, the burst of neutrinos arrives ahead of the visible light by hours, sometimes more, depending on how long the shockwave takes to break out from the dying star's surface. If multiple detectors register a sudden unusual spike in neutrino events at the same time, the system flags the event as a likely supernova. Computers at the Central Coordination Point Cross check the data. If the signal is consistent with a real cosmic source, an automatic alert goes out to astronomers worldwide. The alert would arrive in your inbox before the light from the explosion reaches Earth. Imagine the scene. A quiet afternoon at the Vatican Observatory. A late evening at Mauna Kea. A cold morning at Cerro Tololo in Chile. Astronomers across the planet receive the same urgent message. A neutrino burst consistent with a galactic supernova has been detected. Probable source, Betelgeuse. Time until visible flash, estimated 3 to 6 hours. Phones light up. Telescopes spin into position. Observatories cancel their planned schedules. Every instrument capable of pointing at Betelgeuse is redirected. Space-based telescopes including Hubble and James Webb begin emergency observation runs. Amateur astronomers with backyard scopes get notifications and start setting up cameras. News organizations get tipped off. Live broadcasts begin. Then, hours later, the flash arrives. In the evening sky over part of the world, Orion's shoulder begins to brighten. Within minutes, the brightness rises sharply. Within an hour, the star is unmistakably brighter than anything else in the constellation. Within a day, it dominates the night. The hours of warning matter for science. Every second of the brightening is captured. The shockwave breakout, the moment when the explosion first becomes visible, is recorded by hundreds of instruments simultaneously. The resulting dataset would be the most detailed record of a supernova ever assembled. Scientists would analyze it for decades. The hours also matter for the public. News organizations would have time to prepare informational materials. Public observatories could plan viewing events. Schools could organize watching parties. Cultural institutions could hold ceremonies. The supernova would be a shared global experience, the kind of event that brings entire civilizations together to look at the same point in the sky. Without the snooze warning, the supernova would still happen, but the response would be more chaotic. Astronomers would scramble to interpret a sudden brightening. Equipment would be slowly redirected. Data would be patchy in the early hours. Some of the most valuable observations of the very first moments of the explosion would be missed. With SNEWS, the world is prepared. The system has been operational since the late 1990s, originally built around a much smaller set of detectors. As neutrino observatories have multiplied, SNEWS has grown more capable. Today, the network can detect a supernova anywhere in our galaxy. Recent upgrades, including SNEWS 2.0, provide better timing precision, more reliable alerts, and integration with global astronomy databases. It is one of the most quietly heroic scientific projects in the world, a network designed to watch for an event that hasn't happened yet in our galaxy at human-relevant timescales in over 400 years. The last time a supernova exploded close enough to be visible to the naked eye was in 1604. Snooze has been waiting since. Whenever Betelgeuse goes, the system will send the message. The world will hear it within minutes. We will be ready. 6 months to a year after the supernova peaks, Betelgeuse's brightness will fade enough to no longer dominate the night. Within 2 to 3 years, it will be difficult to spot with the naked eye. Within a decade, it will be invisible without telescopes. Orion will lose its shoulder. For thousands of years, the constellation has been recognizable by its 3 belt stars and 2 bright shoulders, 1 red and 1 blue. Bellatrix marks the left shoulder. Betelgeuse marks the right. The contrast between the cool red giant and the surrounding hot stars made Orion one of the most distinctive patterns in the entire sky. After the supernova, that pattern will be permanently broken. Stargazers a generation from now will look up and see an Orion that is missing something. The belt will still be there. Rigel will still anchor the foot. Bellatrix will still mark the other shoulder. But the upper right corner of the constellation will be empty, or at most occupied by a faint, fuzzy nebula glowing dimly in the spot where the giant once burned. Cultural impact is hard to overstate. Across the world, the constellation of Orion has been recognized in ancient civilizations. The Egyptians associated it with the god Osiris. The Greeks saw it as the Great Hunter. The Babylonians built it into their celestial mythology. Some Native American tribes saw it as a hunter or a warrior. In Japan, it was sometimes seen as a hand drum. In China, the 3 belt stars represented a high official's clothing emblem. For all these cultures, Betelgeuse was usually a key part of the figure. The red shoulder, the bleeding wound, the spot of fire. Many of the stories built around Orion incorporated Betelgeuse's colour and brightness specifically. Removing the star changes the constellation's character. After the supernova, new stories will emerge. The constellation will be redrawn. Schoolchildren learning about the night sky will be told that Orion didn't always look the way they see it. Older star charts will become historical artifacts, showing a configuration that no longer exists. Astronomy textbooks will have to be rewritten. The cultural change will be slow, but profound. Generations born after the supernova will know Orion only as the constellation without a red shoulder. Older generations will remember the way it used to look. There will be a brief overlap, perhaps a decade or 2, when both views coexist. Then the old configuration will fade from living memory. The remnant nebula, slowly growing over centuries, will become its own cultural object. People will tell stories about it. New names will be given. Tourists will travel to dark sky regions specifically to see the place where Betelgeuse used to be. Photographers will capture the nebula's expanding wisps and filaments. Scientists will publish papers about the gas dynamics, the heavy element distribution, the central neutron star or black hole. There's even a possibility that the supernova will accelerate a renewed public interest in astronomy. The last time a nearby supernova was visible was in 1604. That event, observed by Johannes Kepler, sparked enormous interest in stellar physics during the early years of telescopic astronomy. A modern supernova at Betelgeuse's distance, visible to a digitally connected global civilization, could trigger a similar surge of curiosity, education, and research. Orion's old shape is part of human memory. When Betelgeuse goes, that shape will become history. But the change won't just be visible in our sky. The story echoes back through history, where past humans glimpsed similar moments. Humans have witnessed nearby supernovae before, but never one this close. The earliest reliable supernova record comes from Chinese astronomers in the year 185. They described a guest star that appeared in the sky and remained visible for nearly 20 months. Modern researchers have identified the likely remnant, a glowing structure called RCW86, about 8,000 light-years from Earth. The original explosion would have been bright, but not overwhelming. In the year 1054, a much more dramatic supernova lit up the sky. Chinese, Japanese, Arabic, and possibly North American observers all recorded a guest star bright enough to be visible during the day for almost a month. At night, the star outshone everything except the moon for over a year. The remnant of that explosion is the famous Crab Nebula, sitting around 6,500 light-years away in the constellation Taurus. The Crab is now one of the most studied objects in astronomy. In the year 1572, a supernova exploded in the constellation Cassiopeia. It became known as Tycho's supernova, named after the Danish astronomer Tycho Brahe, who studied it carefully. At its peak, the new star was as bright as Venus and visible during the day. The event helped revolutionize European astronomy by showing that the stars were not unchanging, contrary to long-held beliefs. In 1604, another bright supernova appeared, this one studied by Johannes Kepler. It became known as Kepler's supernova. The explosion was visible for over a year and provided some of the best data on stellar death available before modern telescopes. The remnant is still visible today, expanding outward in a beautiful pattern of filaments and shells. After Kepler's supernova, the nearby galactic supernova record went silent. For more than 400 years, no supernova bright enough to be seen with the naked eye has erupted in our galaxy. There have been supernovae in other galaxies, including the famous SN 1987A in the Large Magellanic Cloud, which was bright enough to study in detail despite being far outside. The Milky Way. But within our own galaxy, the last spectacular event happened during the time of Galileo. This silence is unusual. Supernovae in our galaxy occur at an average rate of 1 or 2 per century. Most of them happen behind dense clouds of dust, hidden from our view. Some of them happen on the far side of the galaxy, where their light is dimmed by intervening material. Only occasionally does one explode in a relatively clear region close enough to be seen easily. We are, statistically, overdue for the next bright galactic supernova. Whether that supernova is Betelgeuse or some other star, the event would be the most significant astronomical occurrence in over 4 centuries. Modern telescopes, satellites, and detectors would capture levels of detail that historical astronomers could only dream of. Live broadcasts, high-resolution imagery, real-time spectroscopy, neutrino detection, full electromagnetic coverage. The contrast with historical observations is striking. When Tycho watched his supernova, he had only his eyes and basic instruments. He recorded brightness changes by comparing the new star to nearby reference stars. His written records, careful and methodical, are still studied today, but they capture only a tiny sliver of what was actually happening in the explosion. A modern supernova at Betelgeuse's distance would generate more data in a single hour than all historical supernova observations combined. We would see the brightening curve at every wavelength. We would track the chemical composition of the wreckage in real time. We would detect the neutrinos and possibly gravitational waves. We would watch the remnant form and grow. Humans have always looked up at unusual stars. The next time one appears, we'll be ready in ways our ancestors could never have imagined. But the meaning of losing this particular star runs deeper than physics. Betelgeuse has been part of human storytelling longer than most civilizations. For at least 4,000 years, possibly longer, people have looked up at Orion and noticed the red star at his shoulder. Cuneiform tablets from ancient Mesopotamia mention it, Egyptian astronomers tracked it, Greek poets wrote about it. Arabic astronomers gave it the name we use today, derived from a phrase meaning the hand of the giant or the armpit of Orion, depending on the translation. When this star explodes, it will be the most familiar object in the sky to suddenly disappear in modern history. That familiarity matters in ways that science alone doesn't capture. People form attachments to stars. They use them for navigation, for timekeeping, for orientation, for storytelling. A bright red star in a known constellation becomes a kind of friend in the sky, something dependable. Betelgeuse has been dependable for human civilization since humans first started watching the heavens systematically. Polynesian navigators used it to cross the Pacific. Mediterranean sailors used it to set their course at sea. Farmers in many cultures used Orion's appearance in the dawn or evening sky to mark planting seasons. The star isn't just a physics object, it's a cultural inheritance, passed down generation to generation as part of the natural background of the world. When it explodes, that inheritance ends. The explosion will be a shared experience, but it will also be a shared loss. The brightness will be incredible. People will gather to see it. Photos will go viral. Documentaries will be made. Generations will remember where they were when Betelgeuse exploded. But after the spectacle fades, the constellation will look different. The hunter will be missing his shoulder. People who walk outside on cold winter nights and look up at Orion will see an empty space, or a faint fuzzy patch where the bright red star used to be. There is something tender about this. A piece of the night sky that has been there longer than nations, longer than written language, longer than agriculture, will be gone. Not gone in some abstract cosmic sense. Gone visually, gone tangibly, gone in a way that any human can verify by stepping outside and looking up. The loss is also a reminder. The night sky we take for granted is not permanent. The stars are alive. They burn through their fuel, change form, age, and eventually die. The constellations we know are temporary patterns that have looked the way they do for only a tiny fraction of cosmic history. Tens of thousands of years from now, all the constellations will look different. Stars will have moved, some will have died, others will have brightened or dimmed. The Orion of the deep future will not be the Orion we know. Betelgeuse's eventual death is the first major change to a familiar constellation that modern humans will witness. It is a preview of the slow transformation the night sky is always undergoing, sped up to a moment we can actually observe. For some, the loss will be sad. For others, it will be exhilarating. For most, it will be both. Saying goodbye to something old. Saying hello to a new chapter of cosmic story. The same supernova that takes Betelgeuse from our sky also forges gold and uranium, also seeds the next generation of stars, also teaches us more about stellar physics than centuries of theory. The death of one star is the birth of new knowledge. The end of one cultural object is the start of another. The supernova will be remembered for a long, long time. What we'll know after the dust settles is more than we have ever known before. So when, exactly, will Betelgeuse explode? The most honest answer is that nobody knows. Estimates range from a few decades to 100,000 years. Some scientists are more confident in the shorter end of that range, others lean toward the longer end. The discovery of Sawaha has shifted the conversation, weakening some arguments for an imminent explosion while strengthening others. The pulsation data suggests the star is in late carbon burning. The companion's existence suggests Betelgeuse is younger than previously thought. Both can be true, both can be uncertain. What we can say for certain is this: Betelgeuse is dying. The dying process is well underway. The star is restless, unstable, throwing off pieces of itself, burning through its remaining fuel. Whether the final collapse happens in our lifetime or in 100,000 years, the process is unstoppable. The end is locked in. When the explosion does happen, here's what will unfold. A few hours before the visible flash, neutrino detectors around the world will register a sudden burst. The snooze network will fire alerts to astronomers everywhere. Telescopes will redirect. News organizations will mobilize. The world will brace itself. Then the flash arrives. In the first hours, Betelgeuse brightens dramatically. Within days, it is visible during daylight. Within weeks, it rivals the full moon in brightness. A single brilliant point of light pinned to the sky. People look up. People photograph. People wonder. Schools cancel classes to take students outside. Religious leaders weigh in. Scientists deliver press conferences. The internet floods with images. Over the following months, the star fades slowly. After half a year, it dims to the brightness of a familiar bright star. After 2 years, it is barely visible to the naked eye. Then, gradually, it disappears from human sight entirely. Orion's red shoulder is gone. The remnant nebula begins to grow. Year after year, the wreckage expands. Gas glows. Filaments form. The central neutron star or black hole settles into its long, quiet existence. Astronomers track every detail. Decades of papers are written. Generations of scientists build their careers around the data. Far away, neutrinos and cosmic rays continue to spread. Some of them eventually reach Earth. Subtle changes in atmospheric chemistry, ice cores, tree rings, record the supernova's signature. Future scientists looking back centuries from now will identify these traces and connect them to the date of the explosion. The heavy elements forged in the blast spread through interstellar space. Over millions of years, they mix with gas clouds and become part of new stars and planets. Some atoms made in Betelgeuse's death may eventually become part of distant worlds. The cycle continues as it has for billions of years. What we'll feel when this happens is hard to predict. There will be excitement. There will be awe. There will be sadness for the lost star. There will be a strange, deep sense of connection to something cosmic, something far beyond our daily lives. People who saw Halley's Comet in 1986 describe a similar feeling. A moment of standing under the sky and being reminded that the universe is enormous and active. A Betelgeuse supernova will be that feeling, multiplied by orders of magnitude. The light of the explosion has been travelling for centuries. It might already be on its way. Or it might still be sealed inside the star, waiting for the iron core to collapse. Either way, the moment of arrival will be one of the most remarkable in human history. We are watching the closest possible front row seat to a stellar death. We are recording the warning signs. We are preparing the instruments. We are listening for the neutrino burst. And when the flash finally comes, the entire planet will look up at the same point in the sky and witness, together, the end of a star that has watched over us for thousands of years. Betelgeuse is destabilizing. The consequences are not terrifying for our planet, but they are terrifying in scale. They are awe-inspiring. They are unforgettable. Keep watching the red shoulder of Orion. One night, it will start to brighten, and the universe will never be the same.